Hi, I'm Andrew Gozillon, and this is some work I've done with my supervisor, Dr. Paul Kerr. It's called Point-Free Templates. So C++ template metaprogramming is actually quite similar to functional programming in a lot of ways because the values are immutable and pure. So it kind of forces like a recursive kind of programming kind of style when dealing with metaprogramming. So this kind of led us to the question, what kind of functional programming stuff can we bring to C++ template metaprogramming to make it kind of more interesting and more powerful in general? And we decided that currying is one of these types of things. Currying can enable interesting features and things like point-free functions. And we believe these point-free functions can be used as type-level lambdas. So we've developed a Clang LibTooling that basically translates pointful templates into point-free templates. So what is currying? Currying is a feature that's common to Haskell, OCaml, and F# and a bunch of other functional languages. Treats multi-parameter functions as a bunch of single-parameter functions. The cool aspect of this is that you don't actually have to have all the arguments at the one time to actually make it evaluate. You can only pass maybe one or two, and if it's not enough for it to evaluate, it'll return a function back to you that requires less parameters. This is called partial application. So this is some Haskell. I apologize for this, since I'm not sure if all you're familiar with it, but in essence, the top function is just an add function. It takes 3 parameters, type A, and then it returns a type A. And the second version applies 2 to this add function, which is partial application, and then assigns it to add 2, which is now a new function that is reduced parameters to 1 parameter, and then it returns a parameter. And then you can see below that it basically assigns 3 to this and add it to 2 equals 5. So basically partial applies, and then you can use this function somewhere else. So it's kind of an interesting feature. Then below it, you can basically replace lambdas in Haskell with curried functions in this case. So basically the same code, just a little bit slimmed down in this case. So what is point-free programming? Point-free programming is a style that basically removes parameters from pointful functions. A pointful function is a function with parameters, basically. So the point-free refers to having no arguments anymore. It does this through kind of combinators and higher order functions. So basically, higher order function is obviously a function that deals with functions, takes functions as arguments, returns functions. A combinator is basically a type of higher order function that kind of manipulates the logic of other functions and allows you to kind of chain them together in kind of a unique kind of style. This can kind of make things more kind of concise and equational because you're kind of just looking at function as it is without having to deal with the function prototypes and stuff like that. But basically currying helps enable this. So here's some point-free functions in Haskell again. Return right basically just takes 2 parameters and returns the right-hand side one. And below it is the point-free version of it, which is return right equals const ID. Const is a function that basically takes 2 parameters and it returns the first parameter and tosses away the second parameter. ID is one that basically just returns itself. So in this case, we're basically just tossing away the first parameter and returning the right-hand parameter, the y. And below that is another kind of example, which basically just flips the x and the y of the function, and returns that, applies return right to it. So in this case, the point-free version of that is basically just the combinator flip on applied to return right, which then kind of simplifies down to f equals flip const ID as a pointful function, which is basically just return right kind of expanded into the kind of point-free version. So lambdas are obviously quite a useful kind of feature in C++ and a bunch of other languages. It basically allows you to make code more concise, remove kind of the needed requirement for definitions and stuff like that. So it makes it, in general, more readable. So for example, we've got the Haskell version there, which basically just takes a function and applies it across a list. And then you've got a C++ version, which is basically doing the exact same thing. It just applies it and adds one to all elements in a list. So this is quite a cool feature, and especially when dealing with higher order functions. But we don't actually have this when you're dealing with, or on its own when you're dealing with C++ templates. So you don't have type-level lambdas at the moment. So we're wondering if we can kind of provide something similar using point-free templates. And that's kind of, I guess, our goal here. So how do we supply currying since C++ doesn't actually have it? Well, we use a C++ template, or our C++ template API. The user-level API is actually quite simple. We've got quote C, quote, and eval. Quote C basically takes a metafunction, and when it is evaluated, it will access the type member and apply all the arguments past it to the type member of a template. Quote is a little bit different. It requires you to have a using alias in between it, because it won't access the type member of a function on its own. It's so you can kind of access other things. So maybe you don't have a template with the type member type. You have it named something else. You can use an intermediate type alias to get access to that when evaluating. Eval basically evaluates a passed-in metafunction and a set of arguments. So you'd be passing in one of these quotes wrapped around the metafunction, and then a set of arguments you desire to give to that metafunction. If you've got enough arguments, it will basically return your evaluated result, which could be a type or whatever, or it will return the query template basically back to you, so that you can then use it and apply arguments later on at a later date. So here's an example. They want to C++. The top level is basically common. It's just the standard common type function wrapped up to showcase kind of this example. And common T here is the type alias that we're kind of using as an intermediate when we're using it with quote. So using common T basically just accesses the type member of common, and then you can see later on that in common Q we just pass common T to quote and get the quote back. And then below that we basically have another version which is using quote C, which is directly accesses the type variable. So you can kind of see it basically just passes common instead of the actual common T here. So it's basically just a way of skipping around having to use a type alias to access the type member on certain occasions. But you're going to have to use a type alias if you are accessing something else separately, like a different member. Queried here basically is showing that you can actually query values on, because common is a template that takes 2 parameters, but in this case is only taking 1, which returns a queried type that we can then use later on at the bottom. So basically these are just case statements that are basically just showcasing that they will return float in all cases, because we're passing an integer and a float to standard common type. So common Q basically we pass int float, it returns a float. So in all cases basically it's returning it the exact kind of expected value. And then at the bottom case we just apply float onto it again, and we've already passed it into it earlier on, so it returns a float. So we kind of need combinators to make point-free functions and with templates and in Haskell. So many of these are actually implemented in Haskell. We've kind of just taken them and implemented them in our template API. For example, we've got id, const, flip, compose, and s. id basically is the identity function. It returns itself once passed it. Const takes 2 parameters and it returns the first parameter. And then flip basically, so basically const is just discarding a value that passed it, essentially. Flip basically just takes a metafunction or a function and then flips the arguments around. So in this case, we're passing z and y to x. Compose basically just chains functions together. It's the function composition operator. Basically pass an x and a y, 2 functions, and then we pass the z to those, and they'll just chain them back into each other all the way along. S in this case is something similar to compose, except for you're taking the third parameter and applying it to 2 functions, essentially. And then you're passing the function from the right-hand side into the other function as an argument. So in most cases, x will take 2 arguments. So the S, K, and I combinators, so K is const, I is ID. These are actually the ski combinator calculus, and they basically kind of have a Turing complete language in themselves, so you can write code pretty much anything, I think, with this but it would be pretty verbose. So what does a point-free function look like in our template API? In this case, we can see that the top, this is the standard common type template we showed earlier. It's basically now queried and point-free, because we just stuck it in a quote and underscore C. And it's going to basically be able to be used with an eval and passed values. And then we've got return T2, which is actually the same as the Haskell version earlier on. It basically just returns the second parameter and discards the first. And you can see that again kind of evaluates to the same thing. So it's eval const ID, and then this can be evaluated with some more types if you want to pass it to it, and it will basically be equivalent to your return T2 type. And then you've got flip free, which is a slightly more complex example, but basically all it's doing is taking an f and it's applying, or it's flipping these arguments around and applying them to a template. So instead of x, y, z, we get x, z, y. And the point-free version of this is actually eval, compose, flip, quote. So it's basically just flipping arguments around and chaining them together to get the end result. From this you can kind of see that point-free functions are actually a little bit complex. You wouldn't really want to write them by hand to an extent. So this is kind of where Clang comes in. We developed a Clang LibTool that basically takes a pointful template and converts it to a point-free template. It's actually based on existing kind of pointful to point-free translators in Haskell. So basically it just takes a C++ header or file or source file, and then a template name, a class name, and a member type alias. So basically, in the above case, we would basically pass it flip3 and then type. Flip3 is the class template name, and type has the member alias. And then basically we'll spit out the point-free version of that template in this case. So this is the pipeline here. So we basically take source code and we convert that. We're using the Clang AST, we convert this to a Lambda calculus. And then this Lambda calculus is passed through a point-free conversion algorithm. And then this point-free Lambda calculus is outputted at the end, and we convert this point-free, well, convert this to a point-free template basically through an algorithm. It's quite simple actually. So, what is our Lambda calculus, our intermediate representation to an extent? It's a very simple one-type Lambda. It's basically as basic as you can get. It has a variable, a Lambda abstraction, and an application. So variables are things like types, operators, and functions, inbuilt functions to the API, like type traits in this case. And a Lambda abstraction is basically a Lambda. It takes a parameter, has a pattern at the top, which basically takes a type, a parameter, and then it's got an expression below that. So it's essentially a function, it's an anonymous function in this case. And an application is basically applying variables or Lambda abstractions to other Lambda abstractions to reduce the overall Lambda. So here's our kind of intermediate Lambda calculus as basically classes. It's pretty simple. We've basically got an expression at the very top, so we can pass anything to any expression in this. So variables have a standard string name, so that's just a type name basically, t, int, whatever you want. And Lambda variable is basically, it takes a variable, standard string name or whatever, in this case, and an expression which can be a variable, Lambda, or an application, basically nest them. And an application takes a left and a right expression and basically applies them together. So a stringified version of this is shown below. And basically, you can see that it's got a Lambda, which takes a t, and then it's got, inside that, this t gets applied to another Lambda, which takes a t2, and then in the end it returns a type t2. So it's basically a pretty simple function. So here's kind of how do we kind of translate this from template to a Lambda? So we can kind of see here that we get, at the top we've got foo, which basically just returns an integer. It ignores a t. It takes a t but ignores it essentially. And you can see that in essence the Lambda resolves to pvar t and then just return an integer. So now we've got bar, which basically just uses the foo above it and applies it to, or applies t to foo to get its result. You can see that it gets pretty similar to the previous example, except from it's now passing back a constant integer rather than a template type t2. So we kind of don't treat type traits like this. We don't go into them and then break them up into a Lambda. We basically just use them as kind of operators. They're fixed. We don't change them at all. Part of this is because they're kind of built into the compiler, so we don't really want to touch with that. Another part is because it's a little bit easier to read if it's just got a kind of template name on it, or basically a type trait. It's an existing type trait, so you know what it is and what it does. You don't have to decipher it in some way. It's basically a lot more readable. So templates to Lambda is basically the main thing we use Clang LLVM for in this tool. So basically parse the file, deal with the AST in some way, we check all the nodes, and we kind of take the information we want from those nodes and then translate it into a Lambda. And then we use that Lambda to pass the point-free algorithm. But in this case, most of our heavy lifting is done by transform to cexpr, which basically takes a node and just parses down it, recurses down it to get all of our information, then returns a Lambda back up to it. There's a free overloaded version of this. Types, exprs, decals, and nested name specifiers basically just fixated on the various types in Clang. So this is how our kind of program kind of steps through, and it's not particularly complex anyway. So basically, we initially push on the passed-in template name and member onto the stack, and then we find the class template from the translation unit decal, and we pass this now to transform to cexpr to get the information from this class template decal, and then the once we're traversing down this, we are looking kind of for information to generate a lambda calculus. But we're also looking for the next node, which is in this case referred to by our member name. So in this case, it would be looking for type probably. Then it would pass that to the next instantiation or the next call to transform to CX, where we just basically progress down like this all the way until we've got our endpoint lambda representation. So the stack itself is mostly to deal with the fact that if you have nested metafunction calls inside of the template, you're going to have to look for them at some point to then convert them. So it's basically just a way to hold information so we can search for those other functions that are nested inside the type call. So these are the kind of Clang AST classes we're kind of looking for to take information from to build up our lambda. So the main two are template specialization type and class template deco. The other four are basically just endpoint nodes. There's a few other nodes, but these are the most important ones at the moment. So class template deco basically takes all the parameters of a class template and creates a lambda, the top level lambda part of it. So basically lambda p var t. The second one should be a T2 in this case, because that wouldn't evaluate to, I guess, compilable code in this case, because it's basically saying it's a template that takes a T and a T. So in this case, it's just basically a template that takes two parameters and returns an integer. And template specialization types are, in this case, applications, because it's usually when you're passing a template parameter or a type to a template metafunction. So it's basically you just applying an argument to a template type. And then we generate app var foo var t. So in this case, it's a t being applied to a template function called foo. And then we've got pointer type here, which basically takes an integer and a pointer and applies it to the integer. We don't really, because pointers aren't really types, we kind of need to deal with them a little bit differently. Basically, any kind of pointer that we deal with is going to be changed to a add pointer, and the inverse for removals as well in this case. Built-in types are obviously just integers, and we just basically return, or well, not just integers, but they're types. So the integer or float, and we're going to return these as an endpoint node wrapped in a var, so it's var int, var float, that kind of thing. Tag expansions are basically variadic template parameters, so we need to kind of register those as well. Template type parameters are basically just parameters that are being passed to template specialization types in most cases, not every case, but in most cases we deal with them. It is going to be in that kind of case. So we just pass back var t2, that kind of thing. So that's kind of the main aspect of what Clang does in this case. The other aspects are basically as kind of melding something from Haskell, which is basically removing all the parameters from a lambda calculus expression. So any lambda p var t or whatever is going to have to be searched for in the below expression, then removed. This kind of algorithms taken from and modified slightly from existing functional languages. For example, Haskell has a point-free I/O, and also has a tool that you can download from Hackage, which is called point-free, basically. And then our algorithm is basically based on Haskell's point-free version. So the main section of this algorithm kind of deals with removing lambda parameters from expressions, like I said previously. So when we're dealing with lambdas, all we're really doing is we're getting a value from the lambda's pattern, and then we're going to search the expression below it for this parameter, and then we're going to deal with it in certain ways depending on whereabouts this parameter is. So for example, at the very, very bottom level, we're mostly going to be dealing with variables. So when we encounter a variable, if we find that this variable matches our parameter, we basically change it to an ID, or we put the ID function in its place instead. However, if it's not found and it's the bottom of the tree, we'll apply a const basically, which basically states pass back whatever value is here. We don't actually care about this parameter anymore. It's been passed in. It can be anything. We'll just ignore it. And then in the applications cases, we basically check a bunch of different things based on which subtree the values from. So if it's on the left side, we'll basically apply a flip, so we can flip it around to the right-hand side of the expression. And then if it's on the right-hand side, then it's already in order, so we don't need to modify anything. We can just kind of apply composes and then just chain them together to get the end result. If it's on the left and right, then that's a value that's basically been passed to two expressions at the same time. So we kind of need to apply S to it, the S combinator to it, which basically does the same. It basically passes values to two different sides of an expression and then combines them together to get the end result. And then we have not found, which basically means that, again, very similar to a variable, we don't really care what's in it, we just ignore it and discard it. And there is special cases, so if the value is found and it's on the very right-hand side, we basically just throw it away because it's going to be corrected anyway. We don't actually need any special functions in this place to get the end result. So this is the very simple kind of scenario where we're converting back from a lambda to a point-free template. So basically, we're just converting a string, or we're converting our classes to a string. So in this case, it's very simple. We basically just wrap eval. Anytime we see an application, we put an eval in its place. And anytime we see one of these inbuilt kind of to our API functions, like flip, const, or ID, we replace that with the template name that we're using for it. So const underscore in place of const is probably the only one that's kind of different. But that'll give you the end result in most cases. And if you've got a inbuilt type, then you just pass the inbuilt type in as a bit of value. So in conclusion, we've applied existing algorithms from and concepts from functional programming language to templates, which is kind of allowed in this case for template-free or point-free template code, which is kind of interesting. And we have created a tool from translating from pointful templates to point-free templates. There's some kind of additional work that needs to be done. For example, we kind of want to do point-free template specialization in the future. Most of the interesting things are formed, or most of the interesting applications for templates are specializations in a lot of cases. But because you kind of need the aspect of being able to fix something to a type, you kind of need a case statement in its place. So we need to kind of consider how we'd implement a case statement when currying, in this case, in our API. And then support for non-type template parameters. We currently don't support values, we only support types, so it's type level, but in the future we may consider supporting like non-type template parameters like integers and stuff like that. That's been done.
Any questions?
How you doing? Interesting talk. I was just curious. Firstly, I didn't hear any mention of Boostana throughout the description, and very much your. I mean, Boostana is about programming with lambdas that return lambdas and do other stuff with lambdas. So I was curious. I know that Louis Dion, who authored it, and probably quite a fair chunk of the Boost community, and indeed some of the standards committee, because some of this stuff's going into C++23, hopefully. It would be kind of interested in a LLVM tool which could take some existing C++ and convert it into from template-based into lambda-based, more as a debugging tool, to be honest, rather than actually practicalities. I was wondering what your comments would be on that.
That's actually an interesting aspect, because we were kind of considering using this as a basis for a proof tool in the future. It's one of the possible avenues for using it. So not working on it just yet, but it is something that might be possible. So I think it's definitely something very interesting.
Thanks.
Any more questions? I think I'll take that as a no then. Let's thank our speaker again.
Thank you very much.